this video, we'll solve an optimization problem. This is the 4.7 pre-class video. Alright, let's start by reading this problem statement. Suppose you want to fence in a rectangular area of 1.5 square miles in a field, then divide it in half with the fence parallel to one of the sides of the rectangle. How can you do this to minimize the cost of the fence? Well, this is an optimization problem because we're trying to minimize the cost, and all we're given is the area that we're trying to enclose with this fence and the shape of the fencing. So let's draw a picture of this shape. Here's our rectangle, but we need to divide it in half with the fence parallel to one of the sides. So there we go. I'll label my horizontal fences as X and my vertical lines as Y. But there could be many variations of this picture because we don't actually know what the values of X and Y are yet. That's what we're trying to figure out so that we can minimize the cost of the fence. But what we do know is that the area is equal to 1.5, right? The area is X times Y for a rectangle, base times height. We also know what the length of the fence would be in terms of X and Y because there's 3 X's and 2 Y's. So the length is 3X plus 2Y. Now we're trying to minimize the cost of the fence. That's the overall goal. The way we would do that is by minimizing the length of the fence used. So we want to minimize capital L. Now this should foreshadow a little bit that we need to take the derivative of L because when the derivative is equal to 0, there's potentially a maximum or minimum there. But right now, L is expressed in terms of 2 variables instead of just a single variable. But we can write it in terms of a single variable by first rewriting our area equation as y is equal to 1.5 divided by x, right? Just solve for y. We can plug that into our equation for L. That would give us L is equal to 3x plus 3 divided by x. Now that our derivative is expressed in terms of a single variable, the variable x, I can take the derivative of L with respect to x. That'd be 3 minus 3 divided by x squared. And observe that this derivative is equal to 0 at x equals to 1. It's also equal to 0 at x equals to negative 1, but x equals negative 1 is negative length. You can't physically have a negative length, so we'll just look at x equals to 1. And this means that potentially there's a minimum L at x equals to 1, but we need to verify that. And how do we verify that? Well, we need to make an extra observation that L is decreasing on the open interval of 0 to 1 and increasing on the open interval of 1 to infinity. Well, how do we know that? We'll look at our derivative and plug in values between 0 and 1, get a negative value for the derivative, which means our slope is negative, which means our function L is decreasing. Then plug in an x value between 1 and infinity, you'd get a positive number for our derivative, which means a positive slope, which means our function is increasing on that interval. So therefore, if L is decreasing from 0 to 1, then always increasing from 1 to infinity, then we're guaranteed that there's an absolute minimum at x equals to 1. So therefore, x equals to 1 mile and y equal to 1.5 miles gives the absolute minimum length of L equal to 6 miles, right? We know x is equal to 1, can figure out what y is from our 1.5 divided by x equation, and we know that L is 3x plus 2y. So there we go. That's the amount of fencing we need. That is 6 miles. And that's the shape we need, x equal to 1 mile and y equal to 1.5 miles to minimize the cost of the fence. All right, that's it for this video. Hopefully, solving that optimization problem warmed you up for class.